Right now, at the very edge of the observable universe, there is something that should not exist. You cannot see it. No telescope pointed at it would show you anything useful. It is too far away and too old, and the light reaching us from that distance has been traveling for so long that it carries information about a universe that was only a few 100 million years old. A universe that, according to every model we have built over the last century, should have contained nothing like what we are seeing. And yet, there it is, confirmed, measured, published in peer-reviewed literature by multiple independent teams who did not want to believe it either. The object is a galaxy, or rather, it is a collection of objects that we are calling galaxies because we do not have a better word for them. They are massive, shockingly massive, mature in a way that nothing at that age should be, structured in a way that our best simulations, running on the most powerful computers we have, cannot reproduce. The astronomers who found them described the experience in terms that scientists rarely use. One said it was like finding a fully grown adult skeleton in a graveyard where the oldest burial was 30 years ago. This is not speculation. This is what the data shows. If this kind of investigation is what you come here for, subscribe now. The investigation begins here. To understand why this matters, you need to understand what we thought we knew. And what we thought we knew is one of the most successful scientific theories in human history. The story of the universe begins, as best as we can tell, approximately 13.8 billion years ago. There was a moment, or more precisely a condition, in which everything that exists was compressed into a state of almost incomprehensible density and temperature. This is called the Big Bang. It is confirmed science. The evidence for it is not ambiguous. In the first moments after the Big Bang, the universe was a plasma, an impossibly hot, impossibly dense soup of particles and radiation, so energetic that atoms could not form. Every time a proton and an electron came close enough to combine into hydrogen, the surrounding radiation immediately tore them apart again. The universe glowed, but it was opaque. Light could not travel through it. Nothing could. It was like trying to see through a wall of fire. This lasted for approximately 380,000 years. Then something changed. The universe had expanded enough, cooled enough, that atoms could finally form and hold together. Protons and electrons combined. The plasma thinned. The radiation that had been trapped inside it was suddenly free to travel. And it did. It traveled in every direction, at the speed of light, and it has been traveling ever since. Today, we can detect it. It is called the cosmic microwave background, a faint glow of microwave radiation that fills the entire observable universe, the oldest light we can see, the afterglow of a fire that burned 13.8 billion years ago. What is important about the cosmic microwave background is not just that it exists, but how smooth it is. When we look at it, when we map it across the entire sky with extraordinary precision, it is almost perfectly uniform. The temperature differences across the entire sky are measured in units of 100,000ths of a degree. Not thousandths, 100,000ths. This uniformity is important. It tells us something about the early universe. Specifically, it tells us that the early universe was almost perfectly smooth, almost perfectly uniform. The seeds of structure, the tiny fluctuations in density that would eventually grow into galaxies, galaxy clusters, and all the large-scale architecture of the cosmos, were there, but they were extraordinarily small. And from this, we built a model, a very good model. The model is called Lambda CDM. The name is not important, what the model says is. It says that after the cosmic microwave background was released, after the universe became transparent, those tiny fluctuations in density began to grow. Gravity pulled matter toward the slightly denser regions. Over time, those regions grew denser still. Gas accumulated. It heated up, collapsed, and eventually, hundreds of millions of years after the Big Bang, the first stars were born. Those first stars were different from the stars we have today. They were enormous, made almost entirely of hydrogen and helium because those were the only elements that existed. They burned hot and fast, and when they died, they seeded the universe with the heavier elements, carbon, oxygen, iron, that would make everything else possible. Those first stars formed in small clumps that we call protogalaxies. Over vast stretches of time, those protogalaxies merged with each other, grew larger, accumulated more gas, formed more stars. Small galaxies became medium galaxies. Medium galaxies collided and merged into large ones. And gradually, this is the key word, gradually, the universe built up its large-scale structure. This process is called hierarchical structure formation. It is the cornerstone of modern cosmology. The universe starts small and simple and builds upward. First stars, then small galaxies, then large galaxies, then galaxy clusters, then the cosmic web of filaments and voids that we see when we map the entire observable universe. And here is the critical word in all of this: time. Hierarchical structure formation takes time, enormous amounts of it. You cannot build a massive, mature galaxy in a few 100 million years any more than you can build a mountain in a week. The physics will not allow it. There is a maximum rate at which gas can fall together, heat up, cool down, collapse, and form stars. There is a maximum rate at which galaxies can merge. There are fundamental speed limits built into the process. The model is precise about this. It makes predictions. It tells us what kinds of galaxies we should find at what distances, which in cosmology means at what times. Because light takes time to reach us, and the further away something is, the earlier in the universe's history we are looking. Looking far is looking back. Looking at something 13 billion light years away means looking at a universe that was only 800 million years old. And at that distance, at that age, our models are clear. Galaxies should be young, small, irregular, still assembling, still accumulating gas, dominated by the blue light of newly forming stars, not the red and infrared glow of old, evolved stellar populations. They should look, in every measurable way, like works in progress. The models are good. They have been tested against observations thousands of times. They have held up. Every major survey of the universe, every deep field image, every galaxy census has broadly confirmed their predictions. Until now. The instrument that changed everything was not, at first, welcomed by the scientific community without controversy. It was years behind schedule. It was many times over budget. It was assembled at a facility in clean rooms so spotlessly sterile that the engineers who worked inside them wore full body suits, because a single particle of human skin oil deposited on the wrong surface could ruin a mirror segment that had taken years to fabricate. The James Webb Space Telescope launched on Christmas Day 2021. It reached its final operating position, a gravitationally stable point 1.5 million kilometers from Earth, 6 months later. And then, in the summer of 2022, it opened its eye. The first deep field image from JWST covered a patch of sky roughly equivalent to a grain of sand held at arm's length. In that patch, there were thousands of galaxies, galaxies behind galaxies, galaxies at distances that would have been at the absolute limit of what the Hubble Space Telescope could detect, now rendered in crisp, detailed color. Galaxies further away than any instrument had ever clearly seen. And the astronomers who looked at that image, who had spent their careers building models of what early galaxies should look like, who knew the predictions by heart, some of them felt something close to vertigo. Because the galaxies at the extreme distances were not behaving the way they were supposed to. They were too bright, too massive, too structured, too red. Too red is important. Infrared light, the reddest end of the spectrum, is associated with old stars. Stars that have been burning for hundreds of millions or billions of years. The light from young, hot stars is blue. A galaxy that glows red in infrared is a galaxy with an established, evolved stellar population. It is a galaxy that has had time to grow old. At the distances JWST was detecting, that should not have been possible. The universe had not had time. The specific observations that caused the most alarm came in early 2023. A team led by Ivo Labbé at Swinburne University of Technology published results in the journal Nature. They had identified 6 objects, 6 candidate galaxies, at extreme distances, corresponding to a time when the universe was between 500 and 700 million years old. The masses of these objects, as calculated from their brightness and spectral properties, were extraordinary. Some of them appeared to be as massive as the Milky Way. One appeared to be even more massive. The Milky Way contains hundreds of billions of stars and has been assembling for over 10 billion years. These objects were doing the same thing in less than 1 billion years. Labbé's team looked at the numbers and could not reconcile them with the models. One of the researchers described the feeling of checking the results. The numbers came back wrong. They ran the analysis again. The numbers came back the same. They checked the instrument calibration. They checked the photometric redshifts, the technique used to estimate how far away something is based on how its light has been stretched by the expansion of the universe. Everything checked out. The objects were real. The distances were approximately correct. The masses were genuinely extraordinary. We were in disbelief, Labbé told journalists later. Some of these galaxies should not have been possible. That phrase, should not have been possible, is one that theoretical cosmologists heard with something between excitement and dread. Because it means one of two things. Either the observations are wrong, which is always possible with a new instrument in its first months of operation, or the models are wrong. And if the models are wrong, the question is which part of them is wrong, and why. The first response from the scientific community was cautious. This is appropriate. Science is supposed to be cautious. Extraordinary claims require extraordinary evidence, and the claims being made about these early massive galaxies were about as extraordinary as cosmology gets. The initial concern was photometric redshifts. Estimating distance by the color of an object's light is an indirect method. It is broadly reliable, but it can be fooled. An unusual dust content inside a galaxy can make it appear redder than it is, which could be misinterpreted as greater distance. A galaxy at a moderate redshift with unusual properties could, in principle, look like a distant galaxy with ordinary properties. To resolve this, the teams needed spectroscopic confirmation. This is the gold standard. A spectrum breaks the object's light into its component wavelengths and reveals specific chemical signatures, emission lines and absorption lines from known elements at known frequencies. These signatures cannot be faked by dust. They tell you exactly how far away something is, to a precision that photometry cannot match. Spectroscopic confirmation takes time. JWST had limited observing hours, and each spectrum required long exposures on faint, distant objects. But gradually, through 2023 and into 2024, the confirmations came in. The galaxies were real, the distances were accurate, the masses were extraordinary. In some cases, the updated masses were even higher than the original estimates. This is not the direction astronomers were hoping for. One particular object, given the designation JADES-GS-Z14-0, was confirmed to have a redshift of 14.32. This places it at a point in the universe's history approximately 290 million years after the Big Bang. It is the most distant galaxy ever spectroscopically confirmed. It is luminous. It contains oxygen, the third most abundant element in the universe today, which requires at least one prior generation of massive stars to have formed, burned, and died, seeding the galaxy with this element. To have oxygen at that age, star formation must have begun extraordinarily early, perhaps within the first 100 million years of the universe's existence. This is confirmed, published, peer-reviewed, not speculation. To understand how deeply this challenges the standard model, consider what the models actually predict for this epoch. Lambda CDM, the standard cosmological model, makes detailed predictions about the mass function of galaxies at any given redshift. The mass function is essentially a count. How many galaxies of a given mass do we expect to see per unit volume of space at this particular point in cosmic history? At redshift 7, 8, 9, corresponding to the universe at roughly 700, 650, and 550 million years old, respectively. The models predict that galaxies should exist, but they should be small. The most massive galaxies at those redshifts, the models say, should contain perhaps a few billion solar masses worth of stars. 10 billion would be exceptional. 100 billion would be essentially impossible. What JWST is finding, in some cases, are objects with stellar masses estimated at tens of billions, and in extreme cases approaching or exceeding 100 billion solar masses, at redshifts where the standard model says such things cannot exist. Think of it this way. The standard model of galaxy formation is like a recipe for a cake. It tells you which ingredients go in what order, and how long each step takes. And it has been validated against thousands of actual cakes, observed galaxies across billions of years of cosmic history. The recipe works. We trust it. JWST is finding what appears to be a fully baked, decorated, multi-tiered wedding cake in the oven at a time when, according to the recipe, you should still be sifting flour. That is what should not be there. Several explanations have been proposed. They range from the conservative to the genuinely revolutionary, and it is worth going through them in order of how much they would disrupt our current understanding. The most conservative explanation is that the mass estimates are wrong. Calculating the stellar mass of a distant galaxy from its observed light requires assumptions about the properties of the stars inside it, how old they are, what the ratio of different stellar types is, how much of their light is absorbed by dust. These assumptions are bundled together in what astronomers call stellar population synthesis models. If the early universe produced stars with systematically different properties than we assume, heavier stars or stars with unusual compositions, then our mass estimates could be significantly inflated. We might be systematically overestimating how massive these objects are. This is possible, but it would require the stars in the early universe to be quite different from what we expect, different in specific ways. And even if we reduce the mass estimates by a factor of 3 or 4, many of the objects would still be uncomfortably massive for their age. The second explanation involves the role of black holes, specifically supermassive black holes. Every large galaxy we know of appears to contain one at its center. The Milky Way's central black hole, Sagittarius Urso A star, contains roughly 4 million solar masses. Some galaxies contain black holes billions of times more massive than our Sun. When matter falls into a black hole, the process is catastrophically energetic. Material in the accretion disk surrounding the black hole is heated to millions of degrees and radiates across the entire electromagnetic spectrum, including enormous amounts of ultraviolet and X-ray light. An actively feeding supermassive black hole, what we call a quasar or active galactic nucleus, can outshine the entire rest of its host galaxy by factors of hundreds or thousands. If some of these early, apparently massive objects are in fact quasar-host galaxies, their light dominated by the glow of a rapidly accreting black hole rather than by ordinary stars, then the stellar mass estimates would be misleading. We would be attributing the brightness to stars that aren't there. This is a real effect. It has been observed in closer, better understood systems. Some of the most extreme JWST detections may, in part, be explained this way. But quasar contamination does not explain all of the objects. Many of them show spectral signatures consistent with ordinary star-dominated galaxies, not with active galactic nuclei. The light looks like stars, not like in falling gas. The third explanation is more interesting and more uncomfortable. What if the standard model is missing a process? Specifically, what if star formation in the early universe was significantly more efficient than we assume? In the standard model, star formation is a self-limiting process. When gas falls together and begins forming stars, those stars emit intense radiation that heats the surrounding gas and pushes it away. This process, called stellar feedback, regulates star formation. It prevents a galaxy from converting all of its gas into stars at once. The overall efficiency of star formation in the universe today is quite low. Only a few % of the available gas in any given region typically gets converted into stars before the process stalls. If, in the early universe, stellar feedback was less effective, if the first galaxies were somehow able to convert gas into stars more efficiently, or if the process was driven by more violent events, like more frequent galaxy mergers, then you could build up massive stellar populations much faster than current models allow. Some theorists have begun working with this possibility. It does not require abandoning the standard model. It requires tuning it, adjusting the parameters governing feedback processes, making the early universe's star formation somewhat more explosive, somewhat more efficient. Run the simulations with these adjusted parameters, and some of the massive early galaxies become less surprising, but only some, and the adjustments required are significant. Larger than most cosmologists are comfortable with. The fourth explanation is the one that requires the most fundamental revision, and it involves something called dark matter. Dark matter is real. This is established science. We cannot see it. It does not emit, absorb, or reflect light, but we can detect its gravitational influence on the things we can see. The rotation curves of galaxies, the bending of light around galaxy clusters, the large-scale distribution of matter in the universe. All of these observations, measured independently by hundreds of different teams over decades, converge on the same conclusion. Roughly 85% of all matter in the universe is dark. It does not interact with light. We do not know what it is, In the Standard Model, dark matter plays a crucial role in galaxy formation. It forms the scaffolding, the gravitational skeleton, around which ordinary matter accumulates. Dark matter clumps together first, forming what we call dark matter halos, and then ordinary gas falls into those halos under gravity and begins forming stars. The properties of dark matter halos, their mass, their density profile, how quickly they form, directly determine when and how galaxies can assemble. The Standard Model assumes a specific type of dark matter, cold dark matter, meaning dark matter particles that were moving slowly relative to the speed of light when the universe was young. Cold dark matter has specific clustering properties. It makes specific predictions about how dark matter halos form, how large they are, and how quickly they can accumulate mass. If the dark matter is not precisely cold, if it has slightly different properties, slightly different interactions, the clustering behavior would change. The halos would form differently, and the galaxies that form inside them would look different. Some theorists have proposed modified versions of dark matter, warmer, more interactive, or with self-interactions, that could produce denser, more massive halos earlier in cosmic history, providing the gravitational scaffolding for the early massive galaxies JWST is finding. Others have proposed modifications to the dark matter model that are even more radical. Fuzzy dark matter, in which the particles are so light that they behave quantum mechanically on cosmic scales, producing halos with different density profiles than cold dark matter predicts. None of these alternative dark matter models have been confirmed, but none have been conclusively ruled out. And the JWST observations have given new urgency to the question of whether cold dark matter, in its standard form, is the whole story. There is a fifth explanation, the most radical one, the one that most cosmologists are reluctant to consider, because considering it means reconsidering something that has been tested more thoroughly than almost anything else in physics. What if the early universe expanded differently than we think? The Standard Model of the universe's expansion is extraordinarily well tested. It is called cosmic inflation, the idea that in a tiny fraction of a second after the Big Bang, the universe expanded by an enormous factor, stretching quantum fluctuations to cosmic scales and explaining the smoothness of the cosmic microwave background. After inflation ended, the expansion slowed, governed by gravity. Then, approximately 5 billion years ago, it began to accelerate again, driven by dark energy. This framework fits the data. The CMB, the distribution of galaxies, the redshifts of supernovae, with remarkable precision. But there is a tension, a growing tension. It is called the Hubble tension, and it refers to the fact that the two best methods we have for measuring the current expansion rate of the universe give slightly different answers. The difference is small, but it is persistent. More than 15 years of increasingly precise measurements have failed to make it go away. If anything, it has gotten slightly worse. The Hubble tension does not directly explain the early massive galaxies, but its existence is a signal that something in our model may need adjustment. And if the model needs adjustment in one place, it may need adjustment in others. Some theorists have proposed that the very early universe, before the CMB era, before the first 380,000 years, had a different expansion history than currently assumed. Specifically, some models involve a period of enhanced expansion, or a different energy density, in the first moments. This would change the rate at which dark matter halos could form, potentially allowing more massive structures to assemble earlier. This is speculative. There is not yet strong evidence for it, but it is being taken seriously, not by fringe scientists, but by people at the center of the field. The JWST observations have given them a reason to revisit assumptions that had not been questioned in decades. The story starts, as many cosmological stories do, with someone looking at something and expecting one result and getting another. The year is 1970. The person is Vera Rubin, an astronomer at the Carnegie Institution in Washington, D.C. The thing she is measuring is rotation curves. A rotation curve is exactly what it sounds like. You pick a galaxy. You measure how fast different parts of it are rotating around the galactic center. You plot the velocity against the distance from the center. That curve is the rotation curve. Now, if you have studied any physics at all, and you do not need much, you know what that curve should look like. We have a very good model for how orbits work. It is the same model that tells us Jupiter orbits the Sun more slowly than Mercury does. It is the same model that tells us the outer planets take longer to complete one trip around the Sun. It is called Keplerian rotation, named after Johannes Kepler, who worked it out in the 17th century, and it works like this. The further from the gravitational center, the slower the orbit. The further out you go, the more the velocity drops off. This is not complicated. This is orbital mechanics as we have understood it for 400 years. If you know where the mass is, you can predict the rotation curve. In a spiral galaxy like the Milky Way, the mass is concentrated in the center, a dense bulge of stars surrounded by a disk that thins as you move outward. This means the rotation curve should look like a hill, fast in the middle, where the stars are dense and the gravitational pull is strong. Then dropping off toward the edges, where there is less mass, exactly the way the outer planets of the solar system move more slowly than the inner ones. Vera Rubin was measuring rotation curves because she wanted to know if the stars in galaxies actually did what the physics said they should do. She had better instrumentation than anyone before her. She could measure velocities at the edges of galaxies with more precision than had previously been possible. And when she plotted the curves, she did not get a hill. She got a flat line. Not slightly flatter than expected. Not approximately hill-shaped with some deviation at the edges. Flat. The stars at the outer edges of galaxies were orbiting at essentially the same velocity as the stars much closer to the center. In some cases, the velocity even increased slightly with distance before leveling off. The curve had no drop. Whatever physics said should happen, whatever the visible mass of the galaxy predicted, was not what was measured. Rubin understood immediately what this implied. For the rotation curve to be flat, there had to be more mass than you could see. Not slightly more, much more. The mass had to keep increasing with distance from the center, even as the visible matter thinned out and disappeared. There had to be something present, gravitationally active, capable of influencing orbital velocities, that was not emitting any light at all. Something invisible filling the space around and beyond the visible galaxy in a large spherical cloud called a halo. A dark halo. A halo made of matter that could not be seen. She published the results. They were, initially, not believed. Not by everyone. The idea that most of the mass in the universe was invisible ran against everything cosmology had assumed. But Rubin was meticulous. She measured dozens of galaxies, then hundreds. Every single one showed the same flat rotation curve. Every single one required invisible mass to explain it. The result was robust and consistent and reproducible by any telescope capable of the same measurements. This is established. This is confirmed. The rotation curves of galaxies do not match what visible matter alone would produce. Something else is there. Rubin did not name the missing mass dark matter. That term had actually been used earlier, tentatively, by the Swiss astronomer Fritz Zwicky in the 1930s in a completely different context, which we will get to. But Rubin's rotation curve measurements were what made the dark matter problem undeniable. Before her work, it was possible to treat the discrepancy as a measurement error or a theoretical gap. After her work, it was not. The data was too consistent, the sample too large, the discrepancy too large. Something was out there, and it was everywhere. The idea that something might be missing from our mass accounting did not begin with Rubin. It began 40 years earlier with a man who was, by all accounts, one of the most difficult personalities in 20th century astronomy, and also one of its most brilliant. Fritz Zwicky was a Swiss-American astrophysicist working at Caltech in the early 1930s. He was interested in galaxy clusters, the largest gravitationally bound structures in the universe, collections of hundreds or thousands of galaxies held together by their mutual gravitational attraction. The Coma Cluster, a collection of more than 1,000 galaxies, approximately 320 million light-years from Earth, was one of his targets. Zwicky wanted to measure the mass of the Coma Cluster. The most straightforward way to do this is to count the galaxies, estimate their masses from their luminosities, and add them up. This gives you the luminous mass, the mass of everything that is shining. Zwicky did this calculation. He also measured the mass a different way. The galaxies inside a cluster are not stationary. They move. They orbit the cluster's center of mass, just as planets orbit the Sun, just as stars orbit the galactic center. If you measure the velocity dispersion, the spread of velocities among the cluster's member galaxies, you can calculate, using a principle called the virial theorem, how much gravitational mass must be present to keep those galaxies bound to the cluster. If the velocities are high, the gravitational pull must be strong, which means the mass must be large. Zwicky measured the velocity dispersion of the Coma Cluster. He compared it to his luminous mass estimate. The two numbers were wildly inconsistent. The galaxies in the Coma Cluster were moving far too fast to be held by the visible mass alone. If the only gravity came from the luminous matter, the cluster should have flown apart long ago. The galaxies should have dispersed into intergalactic space. But there they were, still clustered, still bound. Zwicky concluded that there must be additional, invisible mass, what he called, in German, Dunkel Materie, dark matter. The phrase was his. His result was largely ignored for decades. This was partly because Zwicky himself was a notoriously abrasive figure who made more enemies than allies. It was partly because the measurement was difficult and the errors were large. And it was partly because the idea was simply too radical. The universe, as most physicists and astronomers understood it, was made of ordinary matter: protons, neutrons, electrons, and the question of where the missing mass came from seemed more likely to have a mundane answer than the exotic one Zwicky was proposing. But Zwicky was right. The Coma Cluster is now one of the canonical examples of the dark matter problem. The velocity dispersion of its galaxies requires enormous amounts of invisible mass to explain. Modern measurements, with far better instrumentation, confirm Zwicky's original conclusion. The cluster contains much more mass than its visible galaxies account for. Something unseen is providing the additional gravity. Zwicky's dark matter and Rubin's flat rotation curves are the same phenomenon observed from different angles. One is the motion of galaxies inside clusters. The other is the motion of stars inside galaxies. Both say the same thing. There is more mass than we can see, and the discrepancy is not small. In both cases, the missing mass outweighs the visible mass by a substantial factor. This is not a subtle effect. This is not a small correction. The dark matter, whatever it is not a minor adjustment to an otherwise complete picture. It is the dominant gravitational component of every structure in the universe above the scale of individual stars. The visible matter, the stars, the gas, the dust, the planets, is the exception. It is the minority. The normal matter we are made of, the matter we can see, the matter every instrument we have ever built is designed to detect, constitutes roughly 5% of the total energy content of the universe. 5%. The rest is dark matter and something even stranger, which we will come to. But first, we need to understand how completely convinced cosmologists are that the dark matter is real, because the rotation curves and the cluster velocity dispersions are only the beginning. In 1915, Albert Einstein published his general theory of relativity. Among its many consequences was a prediction that had no precedent in classical physics. Mass bends spacetime, and light, which travels through spacetime, therefore bends around massive objects. This effect is called gravitational lensing. The first confirmation came in 1919 during a solar eclipse, when Arthur Eddington's expedition measured the positions of stars near the sun's edge and found they were shifted by exactly the amount Einstein's equations predicted. The mass of the sun was bending the light from stars behind it. What works for the sun works for anything with mass. A galaxy has far more mass than the sun. A galaxy cluster has vastly more mass than a single galaxy. Gravitational lensing by galaxy clusters should therefore be significant, large enough to distort the images of background objects, to bend light from distant galaxies into arcs and rings and multiple images. And indeed, this is precisely what we see. The Hubble Space Telescope has imaged dozens of galaxy clusters showing dramatic gravitational lensing effects. Distant galaxies whose light has been bent into long, curved arcs by the mass of the foreground cluster. Rings of distorted light called Einstein rings, where a background galaxy is almost perfectly aligned with a massive foreground object. Multiple images of the same galaxy appearing in different positions around the lensing cluster because the light has been bent along different paths. The critical fact about gravitational lensing for the dark matter problem is this. You can use the degree of lensing to measure the total mass of the foreground object. The stronger the lensing, the more mass is bending the light. You measure the distortion, you apply Einstein's equations, you get the mass. And the mass you get from gravitational lensing is consistently, dramatically higher than the mass you get from adding up the visible matter. By how much? Typical galaxy clusters contain 3 to 5 times more dark matter than ordinary matter. Some show even higher ratios. The lensing does not lie. It is light being physically redirected by gravity, and the only thing that produces gravity at these scales is mass. The mass must be there, and since it does not show up in any optical, radio, X-ray, or infrared image, it is dark. What makes gravitational lensing particularly powerful as an argument is that it is an entirely independent method from rotation curves and velocity dispersions. It uses a completely different physical phenomenon, the bending of spacetime by mass, measured by a completely different observational technique using completely different instruments. 3 independent methods: rotation curves, velocity dispersions, gravitational lensing. All 3 produce the same answer: more mass than we can see, much more. But the most striking single observation in the history of dark matter research is not any of these. It is something that happened in 2006, when the results from a collision between two galaxy clusters were published, and they changed the argument in a fundamental way. The galaxy clusters in question are collectively called the Bullet Cluster, though the official designation is 1E0657-558. They are located approximately 3.7 billion light-years from Earth. What is unusual about them is not their distance or their mass. What is unusual is that we are observing them at a moment just after a high-velocity collision. Two galaxy clusters pass through each other at around 3,000 kilometers per second. That collision happened long enough ago that the aftermath is clearly visible, but recently enough that the components have not fully separated. What we can see spread across the merged region is a complex mixture of visible galaxies, hot gas, and, if the dark matter hypothesis is correct, a large amount of invisible mass. Here is what makes the Bullet Cluster so important. When two galaxy clusters collide, the different components behave differently. The galaxies themselves, vast as they are actually surprisingly diffuse when seen at the scale of a galaxy cluster. The space between individual stars within a galaxy is enormous, so the galaxies inside each cluster, during the collision, largely pass through each other without interacting. Stars do not collide. The galaxies slow down slightly from gravitational interaction, but they continue outward. The hot gas, the intracluster medium, which makes up the majority of the ordinary matter in a cluster, far more than the stars, does not pass through. Gas has pressure. It interacts electromagnetically. When the hot gas from two clusters collides, it slows down dramatically, piles up, and forms a shockwave. The gas is visible in X-ray observations as a bright region concentrated near the center of the merged system. The distinctive bullet-shaped shockwave gave the system its name. So, after the collision, we have two components of ordinary matter in two different positions: the galaxies, which have moved outward, and the hot gas, which has piled up in the center. We can see both of these directly: the galaxies in optical images, the hot gas in X-ray images. Now, we need to locate the mass. We use gravitational lensing, the same technique as before, to map where the mass is concentrated. And the mass map does not match the X-ray map. The mass is not concentrated in the center, where the gas piled up. The mass is concentrated in two separate clumps, one on each side of the center, corresponding to the positions of the two galaxy clusters after they passed through each other. The mass is where the galaxies went, not where the gas piled up. This is extraordinary. The ordinary matter, the gas, which represents most of the ordinary matter in the cluster, got stuck. It slowed down. It piled up in the center. But the gravitational mass kept going. The mass separated from the ordinary matter. If the dark matter hypothesis is correct, this is exactly what we should see. Dark matter does not interact electromagnetically. It does not interact with the hot gas. It does not slow down in a collision. It passes through, carrying its mass forward with the galaxies. The dark matter from each cluster continued outward, leaving the slowed-down gas behind. The lensing maps the mass to where the dark matter went. If there is no dark matter, if the additional gravity comes not from invisible matter, but from some modification of how gravity works, then the mass cannot separate from the gas. The mass of a system is its mass. It cannot separate from itself. Modified gravity theories predict that the mass should stay where most of the ordinary matter is, with the gas in the center. That is not what is observed. the bullet cluster is not the only cluster collision that has been analyzed this way. Dozens of similar systems have been examined since 2006. In essentially every case, the lensing mass is found near the galaxies, separated from the hot gas, consistent with dark matter that does not interact electromagnetically and therefore does not slow down in a collision. This is the observation that most clearly distinguishes dark matter from the main alternative explanations. This is the observation that most cosmologists cite when they say they are convinced dark matter is real. Not a rotation curve, which might theoretically be explained by modifying gravity. Not a velocity dispersion, which involves assumptions about equilibrium. A direct visual separation of mass from ordinary matter during a collision. Documented. Confirmed. Reproduced in multiple systems. The dark matter is real. The question that remains is what it actually is. If you want to understand what dark matter is, you need to understand when it was important, not just now, in the gravity of galaxies, but at the very beginning, in the first few 100,000 years of the universe's existence. When the universe was young, it was hot, extremely hot, dense. The matter and radiation inside it were a single interacting fluid. Photons, protons, electrons, and whatever the dark matter is, all mixed together in a seething, opaque plasma. This was not a quiet state. There were density fluctuations, regions slightly more dense than average, and regions slightly less dense. Where there was more ordinary matter, gravity pulled it together, but the pressure of the photon matter fluid pushed back. The result was oscillations, acoustic waves rippling through the plasma, like sound waves, but made of matter and radiation rather than air. These acoustic oscillations left an imprint. As the universe expanded and cooled, the photons decoupled from the matter. The plasma became transparent, and those photons streamed freely for the first time, carrying with them the pattern of temperature fluctuations from the acoustic oscillations, frozen at the moment of decoupling. Those photons are still traveling today. We call their distribution across the sky the cosmic microwave background radiation, the CMB. They were emitted approximately 380,000 years after the Big Bang. They have been traveling ever since. We can detect them with microwave telescopes, and they arrive from every direction with almost exactly the same temperature, 2.725 degrees Kelvin. Almost exactly, but not quite. The tiny temperature variations in the CMB, differences of about 1 part in 100,000, encode the entire early history of the universe. They are the baby picture of everything, and they are extraordinarily sensitive to the amount and nature of the matter present at the time they were created. Here is the key distinction that the CMB reveals. Ordinary matter, protons and neutrons and electrons, interacts with photons. It is coupled to the radiation. It participates in the acoustic oscillations. Dark matter, if it exists as the dominant cold, non-interacting component cosmologists hypothesize, does not couple to the radiation. It does not participate in the acoustic oscillations in the same way. It simply provides gravitational pull. It deepens the potential wells into which the ordinary matter oscillates. The shape of the CMB power spectrum, the pattern of how the temperature fluctuations are distributed across different angular scales, is sensitive to both of these components. It tells you not just the total amount of matter, but the ratio of ordinary matter to dark matter and the properties of each. The WMAP satellite, launched in 2001, mapped the CMB with unprecedented precision. The Planck satellite, launched in 2009, mapped it with even greater precision. Both missions produced detailed power spectra, plots showing the amplitude of temperature fluctuations at each angular scale. Those power spectra are not consistent with a universe containing only ordinary matter. The pattern of peaks and troughs in the spectrum, their positions, their heights, their relative amplitudes, requires a component of non-interacting gravitational mass to fit. That component is dark matter. When cosmologists fit models to the Planck data, the best fit has the universe composed of approximately 5% ordinary matter, 27% dark matter, and 68% dark energy, which is a separate mystery we will reach. This is a completely independent measurement from anything involving galaxy rotation or cluster dynamics or gravitational lensing. It uses the physics of sound waves in the early universe, imprinted on photons that have been traveling for 13.8 billion years. And it says the same thing. Dark matter exists. Its abundance is approximately 27% of the total energy budget of the universe. Its ratio to ordinary matter is roughly 5:1. 5 independent lines of evidence: rotation curves, velocity dispersions, gravitational lensing, cluster collisions, and the CMB power spectrum, all pointing to the same component, all quantitatively consistent with each other, all independently derived. This is the most well-confirmed thing we do not understand. Before we ask what dark matter is, it is worth establishing what it is not. Because the first instinct, when told there is more gravitational mass than luminous mass in the universe, is to wonder, could it be ordinary matter that is simply dark? Ordinary matter that is not glowing? Dim stars, failed stars, black holes, neutron stars, cold gas clouds, rogue planets, things made of protons and neutrons, just not shining. Astronomers have a collective name for these objects: MACHOs, for massive astrophysical compact halo objects. In the 1990s, there were serious observational programs to look for them. The technique used was gravitational microlensing. If a massive compact object passed between us and a background star, it would briefly brighten that star through gravitational lensing. A distinctive, symmetric, brightening, and fading that is hard to fake with other astrophysical processes. Surveys of the Large Magellanic Cloud and the galactic bulge looked for these microlensing events. If dark halos were made of MACHOs, compact objects between roughly planetary and stellar mass, there should be many such events. There were some, fewer than expected. The surveys concluded that MACHOs could account for perhaps 20% of the dark matter inferred in the Milky Way's halo. Not 100%, not even close to 100%. The galactic dark matter cannot be made of ordinary compact objects of the right mass range to produce the expected microlensing signature. But there is a deeper argument, one that does not depend on surveys or telescopes, one that comes from the physics of the early universe. In the first few minutes after the Big Bang, the universe was hot enough for nuclear reactions. Protons and neutrons combined to form the first atomic nuclei, primarily helium with trace amounts of deuterium, helium-3 and lithium-7. This process is called Big Bang nucleosynthesis, and the abundances of these light elements that it produces are extraordinarily sensitive to the density of ordinary matter, baryonic matter, the technical term for matter made of protons and neutrons. At the time of nucleosynthesis, we can measure the primordial abundances of these elements. We look for very old, very metal-poor stars and gas clouds, systems that have not been significantly altered by later stellar processes, and we measure the helium and deuterium fractions. The numbers we get match the predictions of Big Bang nucleosynthesis at a specific baryon density. That density is consistent with ordinary matter making up roughly 5% of the total energy content of the universe. Not 30%, not 32%, 5%. The ordinary matter, all of it, every proton, every neutron, every atom in every star and planet and gas cloud in the observable universe, adds up to about 5%. The dark matter, at 27%, is 5 times larger. It cannot be made of protons and neutrons, because if it were, the deuterium and helium abundances would not match. Big Bang nucleosynthesis provides a precise measurement of the total baryon budget of the universe, and it is too small to account for dark matter. So, whatever dark matter is, it is not ordinary matter in a non-luminous form. It is not cold gas. It is not rogue black holes, at least not in sufficient quantity. It is not dim stars or failed stars. It is something else. Something whose particles do not interact with photons, do not interact with atomic nuclei in the way protons and neutrons do, but do have mass and therefore gravity. Something new, something outside the standard model of particle physics. The inventory of known particles that physicists have assembled over the past century. Whatever dark matter is, it is not in that inventory. If dark matter is not ordinary matter, then what is it? Physicists have proposed candidates. Some of these proposals are elegant and well motivated by independent theoretical considerations. Some are more speculative. None have yet been confirmed. The most widely studied class of candidates is called WIMPs, weakly interacting massive particles. A WIMP is a particle with mass in roughly the range of 1 to 1,000 times the mass of a proton, the electroweak scale, as particle physicists call it. It interacts with ordinary matter only through gravity and through the weak nuclear force. It does not interact through electromagnetism, which is why it does not absorb or emit light. It does not interact through the strong nuclear force, just gravity and the weak force. The appeal of WIMPs is not arbitrary. In the 1970s and 1980s, theoretical physicists developed a framework called supersymmetry, which proposes that every known particle has a supersymmetric partner. Supersymmetry was developed to solve problems in particle physics that have nothing to do with dark matter. Problems about the stability of the Higgs boson mass, about the mathematical structure of quantum field theory. It was motivated by particle physics alone. But when you do the calculation of what the lightest supersymmetric particle would look like, you find something striking. It would be stable. It would interact only through gravity and the weak force. It would have mass in roughly the electroweak range. And if you calculate how much of it would have been produced in the early universe, you find the answer, roughly the right amount to be the dark matter. This is called the WIMP miracle. The fact that a particle motivated entirely by particle physics happens to have exactly the properties needed to be the dark matter, in exactly the right abundance. This coincidence made WIMPs the leading dark matter candidate for 3 decades. It motivated an enormous experimental effort to detect them, directly, using underground detectors designed to catch the rare recoil of a nucleus when a WIMP bounces off it. Indirectly, by looking for the products of WIMP annihilation in regions of high dark matter density like the galactic center. At particle accelerators, by producing WIMPs in high-energy collisions at the LHC. None of these experiments have found a WIMP. This is not a small thing to acknowledge. The direct detection experiments have become extraordinary. The Lux-Zeppelin detector, located nearly a mile underground in the Sanford Underground Research Facility in South Dakota, is a 10-ton tank of liquid xenon, surrounded by layers of shielding and monitoring systems, operating at cryogenic temperatures in an environment so quiet that the researchers can measure individual interactions. It is sensitive to WIMP nucleus collisions at cross-sections orders of magnitude below what was theoretically expected. No signal. No excess events above background. No WIMPs. This does not mean dark matter is not WIMPs. It means WIMPs, if they exist, interact with ordinary matter even more weakly than expected, or they are outside the mass range the current detectors are optimized for, or the theoretical models that predicted the cross-sections were wrong. The parameter space is narrowing. The original, most natural WIMP models are in serious tension with the experimental null results. But WIMPs are not ruled out. The detectors are still running. The search continues. The second major class of candidates is axions. Axions were proposed in 1977 by Roberto Peccei and Helen Quinn, and named by Frank Wilczek, to solve an entirely separate problem in particle physics, the strong CP problem. Without going too far into the details, the strong nuclear force has a free parameter, a number in the equations, that should, for no known symmetry reason, be able to take any value. But experiments find that it is extremely close to zero. This is called the strong CP problem. Why is this parameter so small? Peake and Quinn proposed a solution involving a new symmetry that, when spontaneously broken, produces a new particle, the axion. Again, this is motivated by particle physics, not by dark matter. The axion was proposed to solve the strong CP problem. But when cosmologists calculated how many axions would be produced in the early universe, they found potentially a lot. Potentially enough to be the dark matter if the axion mass is in a very small range. Much, much lighter than WIMPs, but not zero. Axion searches use different technology than WIMP searches. Axions can, under the right conditions, convert into photons in the presence of a strong magnetic field. Experiments called haloscopes use powerful resonant microwave cavities in strong magnetic fields to look for this conversion. The ADMX experiment at the University of Washington has been searching for axion dark matter for years and has placed constraints on axion masses and couplings across a range of frequencies. No axion has been found, but the accessible mass range is still limited, and the search continues. There are other candidates: sterile neutrinos, hypothetical heavier cousins of the known neutrinos, which might interact even more weakly; primordial black holes formed in the very early universe before any stars existed, which would be dark and gravitationally active. These are constrained, but not entirely excluded in certain mass ranges. Fuzzy dark matter, an extremely light boson with a mass so small that its quantum mechanical wave properties are significant on galactic scales, which would produce different structural predictions from WIMPs and might explain some anomalies in galactic substructure. Kaluza-Klein particles from theories with extra dimensions. Gravitinos from supergravity theories. The list is long. The field is creative. And the honest summary is this: we have a detailed, precisely measured, observationally robust phenomenon, dark matter, and we have no confirmed particle identity for it. Every motivated theoretical candidate remains undetected. The phenomenon is real. The explanation is unknown. To understand where dark matter is, you have to understand the large-scale structure of the universe. The universe is not uniformly filled with galaxies. Galaxies cluster. They form groups, clusters, and superclusters. And the distribution of these structures across the universe is not random. It is organized. galaxies preferentially exist along vast filaments, sheets and strands of matter that crisscross the universe like the skeleton of some unimaginably large foam. Between the filaments are enormous voids, regions of space almost entirely empty of galaxies, measuring hundreds of millions of light-years across. This structure, filaments, nodes, and voids, is called the cosmic web. The cosmic web is not visible to the naked eye, and not because it is faint. The individual galaxies in it are perfectly visible, but to see the web, you need to survey hundreds of thousands of galaxies, measure their three-dimensional positions, and plot the whole structure at once. When you do, something extraordinary emerges. The universe, on the largest scales we can map, is threaded with structure. Nodes where filaments intersect, containing the most massive galaxy clusters. Filaments connecting those nodes, and between them, vast emptiness. The cosmic web is made of dark matter, not entirely. The galaxies and gas that trace the filaments are ordinary matter, but the filaments themselves, the scaffolding, the gravitational infrastructure that ordinary matter falls into, are dark matter. This is what cosmological simulations show, and those simulations are one of the most powerful arguments for dark matter that exists. When you take the initial conditions of the early universe, the tiny density fluctuations imprinted on the CMB, and you run a simulation forward in time using only gravity, and you include both ordinary matter and dark matter in the proportions the CMB measurement implies, you get a cosmic web that looks like the one we observe. The same filaments, the same voids, the same cluster masses, the same large-scale topology. When you run the same simulation without dark matter, with only ordinary matter, you get something different. The structures are less pronounced, the filaments are thinner, the clusters are less massive. The whole architecture is less organized. It does not match what we see. The dark matter is the scaffolding. Ordinary matter, being subject to gas pressure and radiation, cannot clump as efficiently on its own. Dark matter, being cold and non-interacting, begins clumping earlier and more efficiently, forming potential wells that the ordinary matter falls into later. Without dark matter providing the gravitational backbone, the large-scale structure of the universe as we observe it could not have formed in the time available. The cosmic web is not just a pattern in galaxy distribution. It is evidence that the dark matter was doing gravitational work in the universe long before any star ever formed. The Millennium Simulation, completed in 2005 by the Virgo Consortium in Germany, used more than 10 billion particles to simulate the evolution of a cubic region of the universe, roughly 2 billion light-years across. The dark matter density field in that simulation, when compared to the observed distribution of galaxies in the same region of the actual sky, matches with stunning accuracy. The same filaments, the same cluster locations, the same statistical properties. That simulation has been superseded by more advanced ones. Illustris TNG, Eagle, the Bolshoi simulation. Each generation more detailed, incorporating more physics, matching observations more closely. And in every one of them, the dark matter is doing the heavy gravitational lifting. It is providing the structure. The galaxies are just the luminous traces of a much larger invisible architecture. When you stand outside on a clear night and look at the Milky Way, you are looking at one galaxy, one bright streak of ordinary matter. What you cannot see is the dark matter halo surrounding it, a roughly spherical cloud extending far beyond the visible disk, containing several times the mass of all the stars and gas combined. You cannot see the dark matter filament connecting the local group, our galaxy cluster, to the Virgo cluster. You cannot see the web, but it is there, measured, confirmed, essential to the existence of everything you can see. Here is what makes this particularly difficult to resolve. The uncertainty does not come from one measurement in one place. It comes from a pattern. Look at a single galaxy at high redshift, and you can explain it away. Unusual object, statistical fluctuation, measurement error. Science is full of apparent anomalies that turned out to be nothing. But JWST is not finding one anomalous galaxy. It is finding many, distributed across different fields, observed at different times, analyzed by different teams using different methods. The pattern is consistent. There are more massive, more evolved objects in the early universe than the standard model predicts, and the discrepancy is not small. Cosmologists have a tool for quantifying how surprising something is. They measure it in units called sigma. 1 sigma means a result is within the expected variation of chance fluctuations. 2 sigma raises eyebrows. 3 sigma is considered evidence for something real. 5 sigma is the gold standard for a confirmed discovery. The excess of massive early galaxies, as of 2024, is estimated by various groups to be at a level of approximately 2 to 3 sigma, relative to standard model predictions. Not 5, not definitive, but substantial. Enough that the standard model cannot simply absorb it as noise. Enough that the people who built the model are actively working to understand it, and the number of confirmed extreme objects keeps growing. Every new JWST observing cycle brings new detections. The sample is not static, it is accumulating, and so far it has not been accumulating in the direction of the problem going away. There is a specific object that deserves more attention, not because it is the most extreme. Other JWST detections may ultimately prove more dramatic, but because of what it implies about when star formation in the universe began. JADES-GS-Z 14-0, redshift 14.32. Age of the universe when the light left, approximately 290 million years. Let us sit with that number, 290 million years. In geological terms, that is roughly the span from the beginning of the Carboniferous period, when the first amphibians were beginning to colonize land, when vast coal forests were forming across what is now Europe and North America, to today. That is how long the universe had existed when this galaxy emitted the light we are currently detecting. And in that span of time, the galaxy had already done all of the following. It had accumulated enough gas. It had formed multiple generations of stars massive enough to live fast, burn through their hydrogen, and die in supernova, seeding the surrounding gas with the heavy elements those supernovae produce. It had formed enough subsequent generations of stars that those heavy elements, including oxygen, are now detectable in its spectrum. It had become luminous enough to be detected across the observable universe. This is not a galaxy at the beginning of its story. This is a galaxy with a history. At 290 million years of cosmic age, it already has a history. And to have that history, star formation must have begun extraordinarily early, possibly within the first 100 million years. The first 100 million years. At that point, the universe had barely emerged from what cosmologists call the cosmic dark ages, the period between the release of the CMB and the ignition of the first stars, when no sources of light existed and the universe was literally and completely dark. The first stars are thought to have ignited somewhere between 100 and 250 million years after the Big Bang. The James Webb Space Telescope may be on the verge of seeing not the first galaxies built from those stars, but the second generation, possibly the first generation. We are looking back to the edges of the cosmic dawn, and what we are seeing there does not look like the simple, early, small systems the models predicted. You might wonder, if the models are wrong, or at least incomplete, what is it like inside the community of cosmologists right now? It is not panic. It is not the dramatic crisis that popular science writing sometimes implies. It is something more interesting and more human than that. It is a field in the middle of a real conversation, a field working through something genuinely new. The theorists are busy. In the past 2 years, the volume of papers attempting to reconcile JWST observations with the standard model, or to propose modifications to it, has grown substantially. Some papers propose adjustments to feedback parameters. Some explore alternative dark matter models. Some look at the role of massive black holes in the early universe. Some propose entirely new physics. This is how science looks from the inside when it encounters something it cannot immediately explain. Not silence, noise, productive noise. The observational astronomers are equally busy. JWST's schedule is heavily oversubscribed. There are far more proposals for observing time than the telescope can accommodate. The community has prioritized programs that will get spectroscopic confirmations of the most extreme JWST candidates, build larger statistical samples, and push to even higher redshifts. The question driving many of these programs is this: how far back can we go before we run out of anomalies? Is there a redshift where things look normal? Or does the excess continue all the way to the edge of what we can see? We do not yet know. The investigation is ongoing. There is another dimension to this story that is rarely discussed in the popular accounts, and it is worth pausing on. The objects that JWST is finding are not just scientifically anomalous. They are, in a precise sense, relics. They represent something that happened once, in one direction, in time, and can never be directly observed in real time. The galaxy, JADES-GS-Z14-0, is not 290 million years old. It is 13.5 billion years old. The light we are receiving left it when the universe was 290 million years old. But the galaxy itself, or whatever has become of it over the subsequent 13.5 billion years, is ancient. It has had more time to evolve, merge, change, and disperse than the entire span of complex life on Earth has existed. Whatever it looked like when it emitted the light we are currently measuring, it no longer looks like that. It may no longer exist as a distinct object at all. It may have merged with other galaxies long ago. It may be part of a galaxy cluster. Its individual stellar populations, its chemical signature, its structure, all of it has changed beyond recognition. What JWST is seeing is a photograph taken before anyone alive was born, of a subject who has since grown old and possibly died and certainly transformed beyond recognition. The photograph is precious, not because it tells us about the subject today, but because it tells us about what the subject was like at a moment we cannot otherwise access. And the photograph is unexpected. The subject does not look like we thought they would at that age. They look older, more developed, more complex, and we do not entirely understand why. The implications, if the JWST observations hold up and continue to accumulate, are significant. The most modest implication is that our understanding of star formation in the early universe needs revision. The efficiency of the process, the role of feedback, the properties of the very first stars, all of these may need to be updated. This would be an important correction, but not a revolutionary one. The Standard Model's basic architecture would survive. The moderately significant implication is that cold dark matter in its standard form is not quite right. The halos that formed in the early universe may have been different from what we predict. Denser, more massive, assembled more rapidly. This would require new physics in the dark sector, but it would not necessarily overturn the Big Bang framework or the broad outlines of cosmic history. The most significant implication, the one nobody wants to state directly, but some are beginning to discuss, is that the standard cosmological model may be missing something structural, something not just parametric, not just a tuning of feedback efficiency or dark matter properties, but something more fundamental about the way the universe expanded and evolved in its earliest moments. The Hubble tension, the early massive galaxies, and a handful of other anomalies that have accumulated in recent years may not be independent problems. They may be symptoms of a single underlying issue that we have not yet identified. The history of physics is full of moments where a collection of apparently separate anomalies turned out to be pointing at a single missing piece. Sometimes the missing piece was elegant, a new symmetry, a new particle, a new geometric principle. And when it was found, everything clicked into place and the field moved forward. We may be at one of those moments. We do not know yet. What makes this particular juncture unusual, and what makes JWST different from the telescopes that came before it, is the rate at which the anomalies are being discovered. Hubble showed us that early galaxies were strange. It showed us enough to generate questions, but JWST is generating answers to some questions and whole new inventories of questions simultaneously. The pace is faster than the field expected. When JWST was being planned and built, the community made predictions about what it would find. Those predictions were based on the Standard Model, plus what Hubble had already shown. The predictions were optimistic in the sense that JWST was expected to find many things Hubble could not. They were wrong in the sense that JWST is finding things that even the optimistic models did not predict. Things that were not merely at the edge of sensitivity, but genuinely outside the parameter space that anyone had seriously modeled. This is rare. In modern science, experiments generally confirm what theory predicts, or they find small deviations that refine the theory at the margins. The discovery of a large systematic deviation, not a single anomaly, but a category of anomalies, at a new frontier of observation is unusual. It is the kind of thing that happens at most a handful of times in a field per generation. The last time cosmology experienced something comparable was in 1998, when supernova observations showed that the universe's expansion was accelerating rather than decelerating. That discovery required the introduction of dark energy, a term for something we still do not understand, and it fundamentally changed the standard cosmological model. It was awarded the Nobel Prize in Physics in 2011. Whether JWST's findings will ultimately require a comparable revision is unknown. What is clear is that the question is now being taken seriously by serious people using the most powerful observational tool ever built. It would be wrong to leave this without being honest about what we do not know. We do not know if the mass estimates for the most extreme JWST galaxies are fully accurate. There are real uncertainties in the modeling. The stellar population synthesis models, the recipes that convert observed light into estimated stellar mass, are better than they have ever been, but they are not perfect, especially for unusual objects in extreme environments. We do not know if there are selection effects biasing what we see. JWST is extraordinarily sensitive, but it cannot see everything. The galaxies it detects are the brightest ones at any given distance. There could be populations of fainter, more typical early galaxies that are entirely in line with model predictions, and we are missing them because they are too faint even for JWST. We do not know which of the proposed explanations, if any of the current ones, is correct. Modified star formation efficiency, alternative dark matter, new inflationary physics. All of these are possibilities. The data so far cannot distinguish cleanly between them. What we know is that something is there that is not supposed to be. Multiple teams, multiple methods, multiple confirmations. The thing is real. The discrepancy is real. And the field is working on it with every tool available. There is a specific instrument being planned that may eventually provide the most important part of the answer. It is called the Extremely Large Telescope, and it is currently under construction on Cerro Amazones in the Atacama Desert of Chile. When it is completed, currently projected for the late 2020s, it will have a primary mirror 39 meters across. For comparison, the primary mirror on JWST is 6.5 meters. The Extremely Large Telescope will be capable of taking spectra of objects that even JWST can only barely detect photometrically. It will be able to confirm or refute, in exhaustive detail, the nature of the most extreme early galaxies that JWST is now finding. The Extremely Large Telescope is not the only instrument in development. The Nancy Grace Roman Space Telescope, a wide-field space observatory with a field of view roughly 100 times larger than JWST's, is scheduled for launch in the next few years. Its strength is not depth but breadth. Where JWST examines small patches of sky in extraordinary detail, Roman will survey large areas rapidly, building up the statistical samples that cosmologists need to test models properly. Roman will find the unusual objects. JWST will study them closely. The Extremely Large Telescope will analyze them in depth. This is how modern astronomy works. Not one instrument, but a coordinated ensemble. Not one observation, but many, cross-confirmed, building toward a picture that is more complete than any single telescope could provide. The picture being built right now is incomplete. It has edges. There are places where it is blurry, where the resolution drops off, where the data runs out. But the edges are closer than they have ever been to the beginning of everything. And in those earliest moments, something is happening that we did not predict and do not yet fully understand. The most significant thing about this discovery, and it is important to say it plainly, is not what it might mean for the models. The models can be revised. They have been revised before and will be again. The most significant thing is what it says about the nature of scientific knowledge at this particular moment in history. We have built, over the last century, an extraordinary framework for understanding the universe. We have measured its age to within a fraction of a percent. We have mapped its contents, ordinary matter, dark energy, with remarkable precision. We have traced its history from 380,000 years after the Big Bang to the present day and confirmed the timeline at dozens of independent checkpoints. The standard cosmological model is not a guess. It is not a first draft. It is the product of generations of astronomers and physicists working with every tool available to them. And then we built a telescope powerful enough to look further and with more sensitivity than anything before it. And what we found was something unexpected. Not something that overthrows the entire framework, but something that sits at its edges and does not quite fit. Something that requires us at minimum, to refine what we know, and possibly to discover something genuinely new. That is what makes this moment unusual. Not the anomaly itself, but the fact that we found it. The fact that our instruments have become precise enough and powerful enough to find things that our best theories do not predict. That has not always been true. For much of scientific history, the instruments lagged behind the theories. We believed things were possible, but could not yet see them. Now, increasingly, the instruments are ahead. They are showing us things the theories have not yet imagined. That is a different kind of science. It requires a different kind of attention. Right now, at the edge of the observable universe, there is a galaxy glowing with the light of billions of stars. That light left the galaxy when the universe was less than 300 million years old. It has been traveling for 13.5 billion years. It passed through the vast emptiness of intergalactic space, through the expanding darkness of the universe's middle age, through the gradual brightening of the cosmic web as galaxies and clusters assembled, through the local supercluster where the Milky Way resides, through the diminishing haze of interstellar gas in our own galaxy's outer disk, through the solar system, past the orbit of Jupiter, past the orbit of Saturn, through the inner solar system, past Mars, past Earth's moon, and down through the atmosphere, attenuated only slightly, because the wavelengths we are observing pass through air with minimal absorption, and into a hexagonal mirror segment on a telescope orbiting a gravitationally stable 1.5 million kilometers from Earth. Where it was focused, split into its component wavelengths, detected by an instrument chilled to 40 degrees above absolute zero, converted into digital data, compressed, transmitted across 1.5 million kilometers to a ground station in Spain, uncompressed, calibrated, pipeline processed, delivered to the computers of astronomers at universities in Cambridge, in Baltimore, in Sydney, in Copenhagen, and analyzed by people who did not sleep well the night they saw the results, because the results said, "This should not be here." And that is, if you think about it, one of the most extraordinary things that has happened in a very long time. Not that the universe is strange, we have known that for a while, but that we have now built something precise enough to be surprised by it. Something sensitive enough to catch the universe doing something we did not expect. Something powerful enough to look at a galaxy 13.5 billion light years away and say, "We measured you, and you are different from what we thought, and we are going to find out why." The telescopes are running. The data is accumulating. The models are being revised in a dozen different directions simultaneously. The conversation, slow, careful, contested in the way that only real science is contested, is ongoing. We do not know what is there at the very edge. Not yet, but we are closer to knowing than we have ever been. And whatever it is stranger than we imagined. That is the most interesting thing anyone can say about the universe. And it keeps being true.